Good morning. Our first speaker of the day is a keynote address from Ramish Narayan of Harvard still. Okay. And the title of his talk is Relativistic Jets from Accreting Black Holes. So without further ado, I'll let you begin. Thank you.
Thanks, Dave. So it's already been mentioned earlier, M87 is the first jet that was actually identified by any astronomer. So I actually pulled out the sentences from Curtis's paper. So this is a 1918 paper, and Curtis was describing the so-called nebulae, whole series of nebulae. I don't think they even knew that they were galaxies at that time. It was just nebulae. There's one nebula, NGC 4486, which is, as you know, this big elliptical galaxy, and he says it's bright, it's got a nucleus, etc., etc. These are the sentences here. A curious straight ray lies in a gap in the nebulosity at position 920, apparently connected with the nucleus with a thin line of matter. That is the jet. Okay? That's the jet that we have been discussing a lot at this meeting, and is going to be the focus of my talk today. This jet, as you know, has now been observed in not just optical, but a whole series of different bands. So the optical itself, an HST image, sort of looks like this. This is really what Curtis saw at much lower resolution. That's the galaxy, that's the straight feature, which is the jet. Because the galaxy is so bright, we don't see the jet all that clearly, though the feature is pretty apparent when you look at it. It's got many knots, lumps of various kinds. There's a nucleus and stuff goes out. So when you look at this jet in other wavelengths, so for instance, here's the Chandra image. It looks pretty much the same. Actually, forget the orientation. This is just being tilted by somebody for some reason. That's the orientation of the jet, and it's the same jet. In fact, all the lumps are at exactly the same place. So these are all famous knots, knot A, knot B, knot C, etc. That's the Chandra image. But radio is where we really see this whole jet system in all its glory. So here, for instance, is a composite taken from Owen's paper, starting with the 90 centimeter image, the longest wavelength image. I think there's a low-fun image, even lower frequency than this. I should have shown it. Anyway, yeah, so there is this big, large lobe-like structure, and I think we'll be talking much more about this when we get to the large-scale structure and the feedback and stuff, starting tomorrow. But then as you look in different wavelengths, you start seeing closer and closer to the center. This is that same linear feature which we saw in X-ray and optical. Then you go further and further in, and you just see the jet all the way down. Here's this beautiful image from Hada et al. And what I'm hoping is that by the time we celebrate the centenary, 2 years from now, of Curtis's paper, there will be an equivalent EHT image, which will be even closer to the center, and we would have completely spanned the whole system, from the horizon scale up to 10 kiloparsec or whatever the scale is. This is, I think, a remarkable object. So this is our, I think, prototypical jet. If we can't understand this, we're not going to understand any other jet out there in the sky. It's a dynamical jet, so when you take multiple images, you can see that things are moving. So in fact, as you know, people have actually seen proper motions, superluminal proper motions. We know it's a relativistic jet. We know it's an edge-brightened jet. This is kind of clear in many images, different wavelengths, the so-called sheet, which produces a lot of the radiation. It's very similar across wave bands, at least all the way from radio to X-ray. It's really the same thing. Lump by lump, you can make a match. So everyone pretty much agrees there is one radiation mechanism that goes at least up to the X-ray, presumably synchrotron emission from magnetic fields. Now there is also TeV emission, very variable emission. That's probably inverse contact. It's hard to imagine that the synchrotron goes all the way up to TeV, but you can never rule it out. Nature can surprise us. But this certainly is a challenge. We need to have the same mechanism that will work at least up to radio. If you try to put M87 in the context of AGN in general, I think it's an LLAGN, low luminosity AGN. It would be called a radio galaxy. It's an FR1 type, right? It doesn't have this edge-brightened lobes. It's a low-power FR1 system. I would call it a blazar, even though it's probably not the TeV emission for me already makes it a blazar. But I just think this is a misaligned blazar. If we were to look at M87 even closer to the pole, I bet it would be a lag. Okay? So I'm going to view this as a blazar, definitely a jet source. X-ray power is, on the scale of things, low power. Kind of goes along with the low luminosity AGN. This is low power compared to the brighter X-ray sources that Chandra has seen at higher redshift. I already mentioned this. It's a relativistic jet, and the superluminal motion suggests Lorentz factors up to gamma of 7. Maybe even more, but at least the parts that we see, where we see rapid motion, it seems to be gamma of order 7. It's variable, as I said, and the TeV is the most remarkable, with variation pretty much on the time scale of the black hole light crossing time. So I had to decide what I'm going to cover in my talk. A little bit of a complication was that, slide by slide, everything I was going to say yesterday, somebody or another covered. Starting with John. John gave half his talk on jets. Come on, John. You're supposed to do disks. But anyway, yeah, so there will be a lot of repeat. Okay, things that you heard yesterday and maybe even day before is going to come again, but hopefully, it just becomes more and more understandable and obvious as we go along. And if it's all boring, I apologize. So I'm going to say something about jets versus accretion mode. I'm going to spend some time on the jet physics. Maybe not show everything that I originally planned, but I'll say a few other things which actually were triggered by talks we heard yesterday. And I'll spend the last bit of my talk on a topic that has not been covered and probably won't be covered in this meeting, on particle acceleration, because that's what finally decides the radiation that you observe. Okay, so let's start with the accretion. It's certainly a low luminosity accretion flow, right? I said it's an LLAGN. If you put numbers, that's obvious. Taking this, well, maybe it's no longer the canonical mass, but let's call it the canonical mass of the black hole, 6.6 10 to the 9. Eddington luminosity is like 10 to the 48 ergs per second. And if you look at the ACD of the nuclear region of M87, this is not in the right units, but you can convert this to luminosities. Pretty much it's kind of at the 10 to the 41 ergs per second with some logarithmic factor when you integrate. So let's say the total luminosity 10 to the 42 ergs per second, radiative luminosity. So it's 10 to the minus 6 Eddington. This is definitely a low luminosity accretion system. Now the suspicion is that most of what we see is really from the jet. In fact, we had a talk yesterday asking, and even in the discussion here, in the end, where is the accretion disk? Have you actually seen the accretion disk? It's a great question. I think that's interesting. We should try to figure that out in the future. In any case, even if you counted all this luminosity as accretion, it's very low luminosity. I would say that it's also almost definitely radiatively inefficient. Now, low luminosity is one thing. When you say radiatively inefficient, what you're saying is it's accreting at a certain rate, but the luminosity is not equal to 10% of m dot c squared. It's much less than 10% m dot c squared. So to make a statement like that, you need the luminosity, which is easy to measure, but you also need an independent estimate of m dot, and this is usually hard in many systems. M87, I think we have some clues. So for instance, the jet, we know what's the power of the jet. The estimates vary a bit, but generally I would say, based on all the stuff that Broderick collected from the literature summarized in this paper, let's just say the jet power is on the order of 10 to the 44 ergs per second, plus minus. Some come a little lower, 10 to the 33 plus, some go up to 10 to the 45. Let's call it 10 to the 44. If you say that jet has to be ultimately somehow or other produced by accretion, and if you just say 10% efficiency, I put a question mark here because I may change my mind on this as I go along, but let's say 10% efficiency. The accretion rate has to be about 10 to the minus 4 Eddington, just to produce that power. The accretion luminosity The total luminosity is 10 to the minus 6 Eddington, and probably the accretion luminosity is a tenth of that. We don't know the fraction, but even if you say all of it is accretion, that's radiatively inefficient. So I would say just from these numbers, the radiative efficiency is on the order of maybe 0.1% in M87. Yesterday, I think Ryan's model had 0.6%, if I remember. Okay, so that order, 0.1 to 1% depends on modeling details, etc. So I would say it is radiatively inefficient. It is accreting well below the Bondi accretion rate. So this is something we have seen in Sagittarius A star. Seems to be true again in M87, that not all of the mass reaches the center, but the change between Bondi and what reaches the black hole is not many, many orders of magnitude, maybe 2 orders of magnitude if you take these numbers at face value. Now, I see kind of a problem with the jet power. So this is something, we have experts in the audience. We should discuss this as we go along. So, as you know, Faraday rotation puts a limit on the m dot. So Kuo's paper said 10 to the minus 3 was an upper limit, m sun per year. Yesterday we heard in Algaba's talk, maybe they've actually measured the Faraday rotation, still questionable, but if you take the numbers, 4 times 10 to the minus 4. Now, if you take this m dot and you say that I've got 100% efficiency to make a jet, I'll still get only 2 times 10 to the 43 ergs per second. Okay? This is full m dot c squared with this m dot. If you really think the jet is at 10 to the 44 ergs per second, this is getting uncomfortably close. I won't say, it rules it out or anything, but it's saying something. It's saying that the jet is probably not more than this. If at all, it's a little less. Maybe the m dot is a little closer to Kuo's limit than Algaba's measurement, or maybe, these measurements do make some assumptions about the geometry of the field and orientation, etc. Maybe you can do something there. And here it is, 100%. This is all with 100% efficiency. This jet is probably being produced with 100% efficiency. We can get around all of these, but I would say taking numbers at face value, this is where we are from observations at the moment. This is a little sideline. It's not really, well, I will just mention this. This again, the Broderick et al. Paper. I said it's radiatively inefficient. Right? There is so much accretion happening. It's not producing too much radiation. In fact, most of it is in the jet. Maybe some of it is from the accretion. But just making it radiatively inefficient is not enough. Because if the object in the center is not a black hole, but actually has a surface, when this radiatively inefficient gas, why is it radiatively inefficient? Because it is so low density that the radiation processes are very, very inefficient. But when the gas comes and hits the center, surface, then it will radiate. You can't bottle up the energy forever. It will come out, and you will see all that radiation coming out ultimately from the surface. In fact, roughly you would expect about 10 to the 44 ergs per second coming out of a surface right in the middle. Question is, where is that radiation? You can predict pretty reliably what it should look like. It should be a black body, pretty much, in the optical. And we know what M87 nucleus in the optical looks like. This is what it is, and this is what it should have been. So there's a nice, cute little argument here which says, to make all the observations work, you need radiatively inefficient accretion, no doubt, but you also need a black hole. You need a horizon to swallow that hot gas before it can radiate. Similar argument has been made also for Sagittarius A star. Possibly it could be done in other systems, but these are the two best systems where arguments like this can be made. So not that we doubted it, it's nice to be, see this confirmation that it is a black hole. Okay, so now let me talk about accretion regimes, just following on from what John said yesterday. So theoretically, we are kind of aware of maybe 3 distinct regimes of accretion. There may be more, okay, but I suspect there's more than this. But these are the ones that have been developed, and we have some understanding of what they do. There's one which is the Shakura-Sunyaev thin accretion disk, and based on comparison with observations and also some theory, it looks like that accretion is limited to some fairly narrow range of m dot in Eddington units between maybe 1% of Eddington and Eddington. Now this boundary may go down to 10 to the minus 3, there's a little bit of fuzziness here, but there is a kind of a limited range of m naught. This incidentally is the radius. And these lines are kind of approximate, okay? This is the theorist's conceptual diagram. M87 belongs to this second branch. These are these ADAF, REAF, hot accretion flow branch. So Sagittarius A star, M87, all the LLAGNs, the VLACs, all low luminosity systems. They're all sitting here. They have low accretion rate. These are radiatively inefficient. They make jets, etc., etc. So in fact, this is the branch we are interested in. And above Eddington, there is, at least theoretically, a regime of accretion. This is called the slim disk or hyperaccretion. Tidal disruption events, it's believed, go into that regime. I suspect some quasars are also sitting there. It would be wonderful if we could prove that, but most people put the quasars here, but I suspect some of them are kind of wandering into that. So that's a different talk for a different meeting. Okay, so this is where we are. And the point about this is they all have jets. M87, of course, is a perfect prototypical example. It's an ADAF system. It has a relativistic jet. But pretty much it looks like, and Louis Ho has shown this, they're all radio loud in the appropriate definition. Sagittarius A star being the one exception where we don't know yet what kind of a jet it has. Presumably it has something, and the EHT will show us. Okay. How do we make relativistic jets? Why are these ADAFs so good for making jets? Here, there are question marks. Do they have jets? Even still a little bit. Some of them probably do, but many of them apparently don't. And what's the difference? Why is it happening? Okay, so here is our current understanding. People have talked about many mechanisms, but I would say pretty much everybody has converged finally on some magnetically driven way of producing jets. So you have some large-scale magnetic field. Somewhere at the bottom or the base near the equatorial plane, it is being rotated by the accretion disk or the black hole or whatever. Rotated, it makes a kind of a spiral pattern going out, and that spiral pattern carries away energy, angular momentum, ultimately it dissipates, produces radiation. This is our jet. And the magnetic field presumably helps to keep this thing coherent over the enormous distances that we see. So that is our overall picture of jets. So I got a nice picture from one of Dave's papers. So this is a torus of gas. This is some threaded vertical field lines. And when this torus starts spinning, rotating or orbiting around the center, those field lines get twisted, and you get a nice twisted pattern carrying away energy and angular momentum. This is pretty obvious, when you thread it in the disk. It's less obvious how you can do it with a black hole. And there's some beautiful, fundamental work going back first to Penrose, who showed that spinning black holes are a source of energy, and you can remove energy from there. And then this Blanford and Stanek famous paper, 1977, which showed actually how it can be done in a real astrophysical system. You have to have magnetic field lines near the black hole, and the spin of the black hole drags space-time, and because of the dragging of space-time, the field lines go round and round. They're forced to go round and round once they come inside the ergosphere. They can't sit still. So since they are forced to go round and round, this pattern is pretty much, has to happen. And you get the jet. But a lot of the current work is showing that this actually works beautifully. And I suspect Sasha is going to spend a lot of time on this in his talk. Not sure, but I'm not going to say too much about this. Here is one big question that everybody keeps asking about. What is the engine behind the jets that come out in these AGN? The powerful relativistic jets. I'm going to look at only of those. Is it coming from the disk, or is it really coming from the black hole? Is the black hole just a central potential that's keeping the disk rotating and the disk is doing all the work, or is the black hole playing an essential role? Now, here is my simple-minded thinking. If you want to have a relativistic jet, gamma 7, gamma 10, gamma 20, even 5, okay? 2 even, 2 is not easy to get. You need to start, okay, you got this magnetic field, but you need to have very low mass loading. So when you start, this magnetic field, the jet essentially is taking all this energy flowing out in the magnetic field and putting it into the gas over a range of distance. But you have to start with energy which is primarily in the magnetic field. You don't want to put a lot of gas there. If the rest mass energy of the gas is comparable to or greater than the energy density of the magnetic field, then there's a limit to how much velocity you can get. Ultimately, energy is conserved along flux tubes, and you can easily calculate and show that you can only get velocity of about half c maybe, but you won't get to gamma 2, 5, 10, 20. You need low mass loading, a lot of power, all in the magnetic field, and just a little bit of gas, so that finally something gets accelerated. To me, it seems field lines coming from a disk, they're going to be mass loaded. It's not easy to just separate out the mass from the field and put all the energy in the field. And the simulations at least show this. Generally, the field lines that come out of the interior of the disk, or the surface of the disk, they tend to be much more mass loaded. They get good velocities, but not relativistic, really relativistic velocities. On the other hand, the field lines that go through the black hole horizon, essentially penetrating the horizon, those are great. Because even if you bring some gas a little bit into this region, a lot of the gas can fall into the black hole, this is the horizon here, and a little bit can go out, and maybe you can also have some mass loading through pair processes and some of the things we heard last evening. But in any case, it is a natural region where you can have a lot of power, and quite naturally there won't be a lot of gas. So I believe when you see really relativistic motion, it's probably coming from the black hole. This could be wrong. Okay, this is my prejudice on this business. So, okay, so we are saying the black hole is probably the source. Accretion disk is it's not a nobody. It also produces outflows. It produces a lot of power. From Yuan made this point in his talk. You can get winds. You can get what we call the disk jet. These can be quite powerful. I think what will distinguish them is they won't go to Lorentz factor 10. They will be good, powerful outflows of energy, momentum, great for feedback, etc. But I think for what we observe in M87 and many other relativistic systems, the power coming out of the black hole seems more promising. Okay, I told Sasha that I won't show this movie. He's watching. And I'll just show a little bit just to kind of remind you, because John showed something like this, not the same movie. He showed another movie. Essentially, this is a black hole. There is a torus of gas going around. This is a simulation. There are magnetic field lines in this loop here. And basically, the point of this movie, there are many points, okay, and Sasha will probably cover more of it as it goes along. The basic point is that you have an organized field like this. This system naturally develops a nice, aligned, oriented magnetic field in the central funnel. And that is going to be the conduit for our jet power. So let me see if I can get this guy started. And I won't let it run all the way. Oh, no, it's the wrong one. Good. So all I want you to watch is, look, right now there's nothing here, okay? No gas, no magnetic field, nothing. MRI kicks in, gas starts accreting, gas brings magnetic field in, and this magnetic field, which was originally a loop, quite naturally develops this large-scale structure. We'll just see. Things keep on piling up in the middle, and these field lines are actually twisted. You're only seeing a section. They're carrying away power, huge amount of power. I'll mention a few numbers as I go along. But the point is, it is quite natural, given the right conditions, quite natural to produce this kind of magnetic field and thereby get powerful jets. It's still an open question. This initial condition is probably very unnatural for a real system. Will a real system actually bring all that field in? John already gave some speculations yesterday. Probably the thick disks can do it, thin disks maybe not.
Ramesh, what are the colors?
Here, well, I think it's density. The color here is density and the black lines are the magnetic field.
And the blue stuff flying out?
Where is the blue stuff flying out?
I think that's just low density.
It's just low density. All this blue is the lowest density stuff. Yeah.
It just looked like there were knots and stuff.
Oh, yeah. There is, some of it is numerical. A lot of it is numerical. But some of it is also just the turbulence. You know, things are fluctuating and shaking around. In fact, if I let this movie run longer, this bundle of field lines will start shaking around. So you can see the instabilities in the jet. It's very interesting stuff.
So Ramesh, while people are asking questions,
This is okay?
why aren't we seeing a helical twist to the?
This is a section. If I were to show a 3D movie, you would see the helical. This is only showing the poloidal component of the field. It's a 2D screen, what can I say? Ask Sasha why he didn't make a 3D movie. Yeah. So, he'll probably show a 3D movie, okay? So, just be patient. Now, this is a very simple, fully non-radiative disk model. The current generation of simulations have gone one more step. Now they're putting more thermodynamics and radiation physics into simulations. So Ressler et al. And Sadowski et al. And we heard yesterday from Ben Ryan. So there are different groups who are now actually trying to do the, well, let us say more realistic heating of the gas, true temperature nature of the gas, radiation processes in the gas. And now we can actually follow what the electrons are doing, what the protons are doing. These are still toy models because you still have to invent prescriptions for the heating. But I think this is the way to go. Hopefully, this will get more realistic with better input physics. Hopefully, EHTV will come in with data, and then, we hope we can start understanding what's going on near the black hole better. This is just to say, stay tuned. This is all very new, but I think this is the next frontier in what's happening in this business. So let me very quickly run through some of the things that are needed to make good, powerful jets. Already mentioned, magnetic field has to be nice and organized. So one way or the other, near the black hole, you need to have a bundle of similarly aligned magnetic field lines, all collected to the center. And once you do that, the disk rotation and more importantly the black hole spin will naturally produce the helical thing you need. It will produce your powerful jet. So the Sasha movie I showed is like this initial condition. One big loop. This figure is actually from the Beckwith et al. Paper. So one nice big loop automatically just brings all of this magnetic field to the center and gives you an aligned jet-like configuration. John showed yesterday, you can start with, pretty weak but vertically oriented field with a large scale structure that will also do the same thing. This will bring it in. See, because the gas is flowing to the center, it automatically tends to collect the field. People still debate whether there is some diffusion process which will allow the field to go out, but certainly for these thick systems, the thick accretion disks, it doesn't seem likely. I find it hard to believe when the accretion is so rapid that the field can escape. So I think these thick systems at least will naturally bring whatever is available. In a real system, what is available may actually start a large radius and come in. How well all that works is open question completely. In the simulations, you start with the field close to the black hole. Now, Beckwith et al. Tried initial conditions quadrupolar. So there's one loop that's doing this and another loop that's doing this. This guy did not make a very good jet. This is not a geometry that's very good for making jets. Because the jet finally needs field lines that go from negative infinity to positive infinity. This geometry does not naturally make that for you. This guy will, okay? So this makes, I would say, modest jet, wimpy jet, whatever. If you make too many small loops, rather than one big loop, that's not good. If you may start with toroidal field, that's not good. So it looks like the geometry of the field is very important. That determines how much of a jet you're going to have. Okay, so that's condition number one. And I would say this is still open, how exactly real systems manage to do this. Second, the strength of the field is important. ideally, you want to be at this mad limit that was mentioned several times yesterday. The mad limit is when you brought so much field to the center that it's beginning to push back on the accretion disk and actually kind of disrupts some inner region of the disk. So you reach a kind of new regime, a kind of a quasi-steady state, where the field is being pushed in by the gas, but the field is pushing out, and the two just keep flowing past each other, and you get a quasi-steady state. And because you've got a lot of strong field, you get a very powerful jet. The actual magnetic field strength that corresponds to the mad limit roughly is given by this formula. So for M87 parameters, it's maybe in the order of 100 to 1000 Gauss. Okay, that's the range, depending on what m dot you choose, what black hole mass you choose expressed. Now, this may not be happening in all systems. Perhaps the more natural thing is something that's at a lower level, still organized, but perhaps not quite as powerful as the MAD. So we decided to call it SANE, Standard and Normal Evolution. You know, this paper, people called us mad, but we couldn't get this published anywhere. And this paper, when I was writing, I said, am I going to call this non-mad? Someone I thought calling mad and non-mad did not sound so good. So I decided to make it sane. Again, the referee didn't like it. Referee said, people will think you're mad. You should not use a word like sane. I don't care, I'm old enough. If people think I'm mad, it's okay. So, let's just say mad is when you reach this maximum field. Sane is anything less, but usually, let us say, quite a bit less, so that the field strength is much lower, but you still have the organized field. So this is important, how much field you have. Finally, once you say the power is coming from the black hole, then obviously the black hole spin is important. And in fact, you go back to the Blandford-Nayak formula, putting in some constants, etc. The power in the jet essentially goes like the magnetic flux squared. This is why the field strength is important. Angular velocity of the black hole squared, or spin parameter squared, roughly speaking. So the more rapidly your black hole is spinning, the more powerful your jet will be. Now, one thing I want you to notice is, from the previous slide, the magnetic field for MAD depends on m dot. Okay? So you can't have an arbitrarily large field with an arbitrarily low m dot. So the m dot will determine how much field, because ultimately what's holding this field is the ramp pressure of the accreting gas. Now, since the jet power goes like magnetic flux squared, it goes like the field squared, therefore the jet power will go like m dot. So this is quite important. P jet is going to be proportional to m dot. So people who say, I don't have enough m dot in the system, I'm seeing a powerful jet, no problem, this black hole will do it for me. This doesn't work. Most rapidly spinning black hole you can take, but if you want to get a powerful jet, you still need to give enough m dot just to keep the field in and get the jet going. So there is this proportionality. And in fact, to get a large P jet, you need a large m dot, you need to be in the band limit, and you need a rapidly spinning black hole. All of these things have to come together to make the thing work. So I've got a little table here, very, very crude. You shouldn't take the numbers too seriously. Basically, if I define a jet efficiency, P goes as eta times m dot c squared, what kind of etas you can get? You can get up to 1, or maybe even 1.5, okay? But 1, let's call it 1. This is the limit when you are in the mad limit for the magnetic field and as rapidly spinning black hole as you want, as you can. This is all, Tchaikovsky's work. You can't get much above 1. I would view this as kind of a limit, how much power you can get from the jet. If you have an opposite limit, low spin and very sane magnetic field, pretty much you get almost no power in this relativistic jet. You can still get a wing, okay? And I just made up numbers for these other columns based on the Sadowski paper. But basically the point is, very weak jet, very strong jet out here. Okay, here's the question that Masa asked me yesterday. Is M87 mad? Actually, I had a slide even before you asked me. Answer is yes. M87 is mad, at least in my opinion. And let me tell you why I think this is. See, earlier I told you, there is this problem already with the jet power. Looks like the jet is very powerful, and yet we have very tight constraints on m dot. And to fit the numbers, already, with great difficulty, you can make L jet and m dot fit, but only if you take 100% efficiency for the jet. Even then it's hard, okay? You're really pushing numbers. So we're talking about 100% efficiency for M87, and if you look at this table, that's down here. So I would say M87 must be mad, and M87 must be spinning rapidly. Otherwise, hard to see how those numbers would match up. Now maybe the numbers will change, but right now, given the numbers, that's what we have. Then we heard talks yesterday, which to me at least just reinforces all of this. See, Keynote mentioned that when they do this spectral fitting with the self-absorption frequency, the magnetic field strength was maybe 300 Gauss in the simple analysis, and you can push it to 100 Gauss. Let's say, a few hundred Gauss. Now, the mad magnetic field strength, given the m dot, is a few hundred Gauss. So again, I think it's really consistent. The measured value is what you require to be a mad system. So here is my answer. Maybe this is going to be the conclusion from this meeting. Maybe we should all write one paper. M87 is mad. It's a combined group paper. But I think it's looking pretty promising. And of course, EHT will tell us that this is true. Now, let me continue with a few other topics. Just in outline, okay? I can't go into any of the details. Collimation. These relativistic jets do not self-collimate, okay? It's a little bit counterintuitive because, I told you that you take this field line and you whip it around and it makes this helical pattern. And you say, look, if I've got a helical pattern of magnetic field, there is a hoop stress, right? Which will be trying to squeeze the jet, and it should automatically self-collimate. This doesn't work like that. In these relativistic jets, especially as you go to the force-free limit, you have to worry about what the electric field is doing, not just the magnetic field. The bottom line is there are actually analytic solutions, like this nice solution from Micron, who basically took a split monopole. So these are magnetic field lines, and you make it spin, and you say, what is the solution? You can get an analytic solution, and that analytic solution will show you that field lines nicely twist round and round because of the twist in the center, but the colloidal structure doesn't change at all. The lines will go out pretty much radially in the colloidal plane. In fact, a lot of the power will go in the equatorial plane. There's nothing that's focusing power in the polar region. So, taking that as a kind of a nice toy problem, one can conclude, and you can do this better. Generally, in the relativistic regime, spinning magnetic fields don't want to just self-collimate. Somebody has to push it in, give it collimation. So it has to be some kind of an external medium that will tell the field, go in this direction, be collimated. And it has to be the accretion disk. If it's a GRB, we know it's probably the star from which the GRB will form. But for our AGN and X-ray binary systems, it has to be an accretion disk itself. So here is a picture, shows there are field lines sticking out of the black hole. If you didn't have any disk, firstly the field lines won't stay on the black hole without the disk. You already saw that. But basically the disk is needed not just to hold the fields in, but also to give them a shape. And that shape comes from the fact that we have a nice, thick, geometrically thick structure, this ADAF, which becomes even thicker because of the wind, which is all flowing out, and somehow all of this does the right job and gives you a collimated shape of the jet. This happens in the simulations. Any number of people have run these simulations. This thing automatically happens. The disk conspires in the right way to produce your collimated jet. Now we are beginning to see even some observational tests. So there is some recent paper by Hada et al. There's also a poster in the SENS poster. People are now beginning to look at, can the ADAF provide enough pressure to hold the jet in? And is the profile looking the right shape to give me the right shape of the jet? I think it's all beginning to look reasonable. I won't say it's proved, but it's all looking pretty good. Now here's the contrast. Thin accretion disk doesn't generally have as much wind, and it's also thin, geometrically thin. So it doesn't have all this collimating action going on. So Dei-Fu Bu's talk was discussing this yesterday. So generally this would suggest that thin accretion disks probably, because of lack of collimation, are less likely to make jets. On the other hand, they may have line-driven winds, and maybe that's all you need. Maybe that's how some of the thin disks have jets. This is all speculation, okay? But I think this will get clarified in the next few years as people begin to do better simulations of thin and thick systems. Okay, so thick systems are good. ADAPs are great for making jets, and this is why all the LLAGNs seem to be radio long. Collimation. So from the picture you can see the collimation is kind of steady and continued. In fact, it's got a parabolic shape in the simplest models. And the observations seem to show a parabolic convergence of the disk. So here are a couple of papers showing the width of the jet versus distance. This is M87. And the width is not increasing linearly with distance. That would be a conical jet. The width is increasing as square root of distance. That's a parabolic jet. So that's very nice, going out to, at least in this case, 1,000 short shield radii, and I think there are other papers that go even further out, etc. Good? Here is something that, the theory is very clear on. When you have these jets, which are being produced and powered by spinning magnetic fields, you don't accelerate instantly to your asymptotic Lorentz factor. Acceleration happens continuously throughout this collimation zone. So you start essentially at Lorentz factor 1, or velocity 0, and then you keep getting faster and faster and faster. And I think in the simplest models, the Lorentz factor is supposed to go like distance square root with some coefficient which will depend on details. And I would say observations are kind of seeing this. There was even, I think, a poster maybe outside, but here are some papers in the literature which show that the velocity and Lorentz factor is increasing with distance in M87. So I think it's kind of hanging together, but here is a clear prediction. If EHT goes in and suddenly sees gamma 10 bulk motions close to the black hole, I think that would be a surprise. It shouldn't happen. In any of these models, near the black hole, you should not have gamma 10. Gamma 10 will come beyond radius 10, 100, further, depending on details. Okay. So that's all I'm going to say on the jet physics in terms of the structure and the dynamics. So in the last 8 minutes, I'll say a little bit about particle acceleration. This, I think, is kind of underrepresented at this meeting. It's an area where really exciting work is being done currently, thanks to developments in, again, computer simulations. We know that we want to make power law distributions of electrons. In M87, it has to produce all the way from radio to X-ray, so it has to go at least up to Lorentz factor of 10 to the 8. People talk about non-thermal processes for acceleration. This is the old standby, right? Fermi acceleration in shocks. Everybody talks about it. This is kind of the new kid. I mean, it's always has been there. People have always said magnetic reconnection. It's beginning to look a lot better in recent times, and I'm going to show a little bit of what has been found in the last few years. The most important work in this area is being done by this technique called particle in cell, PIC, where you are essentially simulating the entire plasma at the particle level. So you're putting particles, you're putting fields on the computer, of course scaled in some way, because you can't do the real system, but it's trying to do the electrodynamics at the most fundamental level, down at electrons and protons. So I'm going to show some results borrowed entirely from my colleague Lorenzo Cironi, who's doing, I think, the best work in this business. Next meeting, somebody should invite him. Okay? Please keep it in mind. He or Dmitry Uzdensky or somebody really knows this stuff. Okay, so first lesson that has come from these PIC simulations is shock acceleration doesn't work very well for relativistic systems. If you have a shock which is relativistic, so that is to say the flows have gamma of several, if you have a magnetized system where the sigma parameter is largish, sigma is basically a measure of how strong the field is relative to the rest mass energy of the gas, okay? And we are thinking of sigmas of 1, 10, etc. for relativistic jets. If sigma is largish, 5 minutes, then shock acceleration just doesn't work. And there's a very simple explanation, but I won't go into it because there isn't enough time. Essentially, particles, if you remember Fermi, are supposed to bounce up and down, up and down. And everything is moving so fast, the particle is unable to come back. It's just being carried away, and the relativity and the magnetic field conspire to make this essentially impossible. So here is a nice, quick simulation which didn't produce any power law. It just produced a Maxwellian distribution of electrons after running it for a long time. So shocks, you can make it work, but you need very, very special conditions in relativistic systems. Reconnection, on the other hand, loves relativistic systems. It works great in that limit. And you all remember what reconnection is. You've got magnetic field lines in opposite directions, and as they come together, they annihilate, and some of that energy in the magnetic field, which is destroyed there, is converted into particle energy. So it accelerates particles, and the particles come squirting out here, and they come with quite large energies. So, once again, this is the parameter sigma, B naught squared over 4 pi. Think of this as rho c squared. And when you do relativistic reconnection, sigma of several or 10 or whatever, you get beautiful power law distributions. So I'm going to show one movie in 2 slides actually, but let's start with this. Islands. The islands collect to become bigger and bigger islands. And you can watch what particles are doing. And so I want you to watch. There'll be a particle, this white circle will start here. It's coming in. At that point, it's hitting the reconnection layer. That's when it got one kick. This is the kick from the reconnection itself. Now here is the particle. It's sitting around in this island. And now watch what happens. It starts bouncing up and down between the islands. Almost like Fermi. And it picks up more gamma.
All these are in current sheet.
These are all in the current sheet region. Yep, current sheet region. But islands are just collecting all the past stuff that's coming in. And so you can get Lorentz factor of 100 on the computer, and in fact the limit, there's no limit. You can get 10 to the 8. Computer won't run long enough, but in nature there's plenty of time. It'll work wonderfully. Okay? One of the nice things about reconnection is that you can get very hard power law distributions. So let me remind you, if you say dn d gamma goes like gamma to the minus p, shocks can't go below 2. In fact, typically they are 2.2, 2.4, they're happy. 2 with very, very idealized conditions. Now, when you see very hard spectra, they often ask for gamma 2. And in fact, they even have systems that want gamma less than 2. Some of the hardest blazar spectra require gamma less than 2. I mean, P less than 2. Reconnection will do it for you. So here are the simulations. You can get P of 1.5 if you want, if you have a sufficiently magnetized reconnection layer. So that's probably one of the big things going for reconnection, apart from its efficiency. I was just looking at spectra, SED of various knots in M87. I'm seeing lots of hard spectra. I don't know how people are modeling these. I have a feeling you need P equal to 2. Eric Perlman is here, he can probably tell us what's the story with these hard spectra. You know, every blob seems to have a pretty hard spectrum. HSV1, spectral index is like half. Half is very tough, I think, with a shock. You can do it, but you really have to push it. And 0.4 and 0.3 is just impossible. Reconnection can do it. So I kind of tend to believe what Lorenzo Cironi is telling me, namely that for jets, probably reconnection is something to take very seriously. It's not that shocks are impossible. Probably they're both there. But shocks have their difficulties. You shouldn't be too relativistic. You shouldn't be too magnetized, and the magnetic field should be in the right orientation. I'm finished. Reconnection is much less restricted. Relativistic is actually good. Magnetic field strength is actually good. These are all really great. It can produce a much wider range of p-values, but it does require this special geometry, which only happens in some places, and you get flares and stuff like that. So I'll just leave it here. I think we need to hear from a specialist on this stuff. So here is the summary. We have this beautiful, perfect, misaligned blazar nearby. Seems to be mad, okay? It's great. We've got a lot of recent progress. GRMHD on the jet formation, PIC simulations and particle acceleration. Both are forging ahead. I think they're all going to come in with lots of new understanding, and then when the observations also make the next leap, I think we're going to, the next several years, we're going to make a lot of good progress. God willing. Okay, thank you.
Thanks very much, Ramish. That was great. Before I open this up to questions, I want to make one comment about the slide that you showed of our paper back in 2001. Actually, those simulations, I was the first author, but those simulations were done by Uchida's star graduate student. No? Masanori Nakamura. So,
I didn't know that.
yeah, well, that's why I wanted to make the announcement. Okay.
Koide's paper is even earlier, is it?
Koide was, he did some simulations in that paper also.
Yes.
I did too.
You did.
But those two beautiful ones were done.
Well
in
done.
process. Okay. First question. I actually saw you, sir, behind. Yes, in the light. Yes.
So this is M87 workshop, but let me ask a question about jet collimation on more high power sources like quasars. Recently I have worked on collimation profile measurement for S3C273. This is a quasar version of M87. It's the first discovered jet and really powerful jet. And I found that the jet is actually collimating within the bonding radius. It's very similar to M87. So my question is that so if the jet from the thin disk have also collimation, how do you read this kind of collimation? On really large scale, something like 10 to 5 such radii. Do you have some ideas about that?
Well, I can always give you some ideas and words, but this is obviously a very important question. Because M87, as you say, is a perfect example of one class, the low luminosity AGN. But we have jets in 3C273, 279, lots of other bright systems. What's going on there? My guess is that somehow or other those guys are producing strong waves to produce the collimation. So one way could be that they are actually slightly super Eddington, and because they are super Eddington, they are thick, geometrically thick, they are slim disks. Slim disks make beautiful jets. Sandowski has shown that. Or they may be sub Eddington, but with line-driven winds that are so strong. I'm not so sure about that, but something like that must be happening. Or there's some other physics that we haven't yet recognized. But thank you, that's an obvious and very important question.
Okay, right here and then up here.
About particle acceleration through the connection. So you mentioned that the spectrum becomes parallel. So why is that? Why it becomes parallel?
Which power?
Parallel spectrum. You said that as a result of acceleration, spectrum becomes parallel. Am I correct?
I think the energy
spectrum.
Energy spectrum becomes parallel, yeah.
Why is that?
Okay, that's a very good question actually, yeah. In Fermi we understand, it's because there is repeated acceleration. So in Fermi acceleration, every time the particle bounces, it gains some energy. Some particles bounce twice, so they gain more energy. Some particles bounce 3 times, they get more. And depending on how many particles have how many bounces, you can get a whole distribution. In the reconnection again, the power law seems to be because it's not a single event. That's why I showed that movie. Go back. That movie will, it's many, many events. It's there's one here, and this particle itself goes through many bounces and events. In fact, it may have additional reconnection events. So I think it's again the collective effect of sequence of small accelerations. Some particles get many of these sequences, and so they get very large energy. And I think it somehow conspires to make a power law. Now, why is it 1.5? Why is it 2? I don't think we have a fundamental understanding. At least I don't. But maybe Sironi can tell us.
Yes, up there.
So if M87 is mad, then it should have very peculiar accretion rate curve, sometimes maybe discontinuous. And the probability and light curve too. Is there any observational evidence that supports M87 mad model in addition to the gamma factor is example?
Nice question, yeah. So as you saw in that picture, once you go to this mad regime, we expect the accretion to come in lumps. Actually, there'll be bubbles escaping. So it's a much more chaotic and time-dependent flow. The problem right now is, like we discussed yesterday, we haven't seen the accretion disk at all so far. At least nothing that is obviously the accretion disk. If and when we see it, and maybe EHT will see it, okay? At least EHT may, if we're lucky, separate out the disk part from the jet part or whatever. Then I think your question will become quite relevant. Do we see these episodic blobs coming in? There's also a question of time scale. The guy to ask is Sasha, who's going to speak next, but he really knows these mad simulations. So one should check the time scale, see how long we have to observe, because M87 time scales are long. But it's a very nice question. I think it's something that should be looked into for the future.
Final?
I mean, you try to drive us mad, I understand. But if you remember Monica's talk yesterday, she was reproducing the radiative properties of M87 with the same model, with standard accretion rates. So is that wrong, or where is the discrepancy here?
Well, the jet power I'm talking about is not the radio power. I'm talking about the jet power that probably we'll hear about tomorrow. 10 to the 44 hertz is not the radio power, that's 10 to the 41. 10 to the 44 is the estimate of the kinetic power in the jet. That's the number that's hard to fit, in my opinion.
Yes, but most of that is based on the large-scale lobes, for example. We did that in our LOFRA paper. And the other argument you could make is that this is time dependence, for example, right? Because this is integrated over 10 millions of years, while we're right now looking at what's the current accretion rate, and that could well be much lower than what you measure over 10 million years.
Much lower is hard.
And
this is something that Broderick looked into, because in that paper we looked at the largest scale, and then 10 kiloparsec, 1 kiloparsec, 50 parsec, I forget what the different distances he looked at, all the way down to HST1, okay? The numbers do change. But it's not like it comes down by a factor of 10 to the 3 by the time you come to HST1. There are still pretty substantial jet powers. How strict the constraints are, I don't know. So we'll have to see.
But as you see, I mean, the only thing you see is the radio emission that you can reproduce. All the other estimates are more or less indirect, right? So that works as the same model. I'm not saying this is absolutely right, but just to say that we all should be mad, I think is maybe a bit of a
well, you guys didn't. I asked a simple question yesterday. What is the power in the center of the spine? And I wasn't able to get an answer. So I bet if you go and look at your model, there will be an enormous power coming out in the middle. Take a look. Go ahead.
About the flat spectra, and so the inefficiency of relativistic shocks in particle acceleration was demonstrated back in the 90s and 2000 by Monte Carlo simulations. And you didn't mention turbulent acceleration. Now that could give the very flat spectra, but looking at the movie that you showed, actually for me that looks like turbulent acceleration.
It's
So-
Fermi type 2, yeah.
It's Fermi, and because people always argue that a relativistic reconnection is like Shop first order, but you see losses here. Sometimes you have peak and some, it's just reconnection, it's
It
just
is
turbulence,
like,
right?
it's like what Fermi thought.
Yeah.
Two molecular clouds coming together and bouncing the particle. It looks just like that, yeah.
So would you agree it's kind of a version of
Kind
turbulent
of.
acceleration?
It's kind of Fermi type 2 acceleration.
Fermi.
These are not the words that they use, okay? But yeah.
Thank you.
Okay, let's give Ramesh a hand again, and thank you very much.